Hello, everybody, and welcome to my class. Uh, and today we will be doing a continuation of last class. So we'll still be doing counting techniques. So, can everybody see my screen? Yes or no in the chat. Can everybody see my screen? Yes or no? Yes. Okay. Very good, Stephen. Uh, so let me go to the first slide. I don't know why it's on the last slide. Okay, so we are going to do counting techniques again, permutations and combinations. But mostly today, we are going to be solving a lot of different problems. I introduced the methods last class, so today we will be using those methods to solve our problems. Okay, so our schedule. First, we're gonna review our methods and definitions of factorial, permutations, combinations. Okay, so for those who have not been to the last class, pay attention during this review session and take notes. But I think most of you have been to last class and have taken notes. So next, we are going to review. We're going to look at the steps to solving problems. Okay, so mostly during probability or counting techniques, we have word problems. Okay, so and important that you read through all of them. So I'm gonna introduce some steps, very basic ones, to help you solve these problems. And lastly, and the third section is gonna be the largest section. We are going to be solving a lot of problems. Okay. So are there any questions about our schedule? Okay, any questions about our schedule? No? Okay. So let's start then. So review factorial. So factorial. So that's basically the product of a specific integer and all the integers below it. Okay. And that's including 1. Okay. So let me give an example. And I use this example a lot, b4 factorial, which equals, okay, 4, right? And it's our specific integer, okay? Then multiply by every integer below it, including 1. You can't go to 0. Does anybody know why we can't go to 0? Okay, who knows why we can't go to 0? Exactly, Stephen. Very good. Because if we multiply by 0, it would be equal to 0. Okay, that's obvious. So we do not go to 0, we just go to 1 in every integer above 1 and between the specific integer. Okay, so let's do another warm-up. 5 factorial, anybody know that? That would be 5 times 4 times 3 times 2 times 1, right? 120, okay? So make sure you know your factorial, because when we go over formulas and combination formulas later, we will be using a lot of factorial, so make sure you know. Let's move on to combinations and permutation. Actually, right here on this specific slide, I have combinations first, but I'm going to explain permutations first because it is easier to understand. So permutations, it's basically the arrangement of a specific linear sequence. So you have this set right here, okay, this linear sequence A, B, and C, okay, A, B, and C. This linear sequence, and we're supposed to permutate it. And we just arranged it, okay, permutate, it's basically arranging this set, these objects in this set. And to arrange it, to permutate it, it's just factorial. Okay, so and it would be n factorial. N factorial. Okay, so n factorial. That is our permutation formula, I could say. So n, what does n equal? Can anybody tell me what n equals in this formula? What does n equal? Okay, Steven says 3. Very good, very good. And Frank as well. Good. So n is the number of objects in this particular set. Okay. And let's say we have A, B, C, and D, then n would be 4. Okay. So n equals n factorial equals 3 factorial, which equals 6. Okay, so n factorial right here. Let me elaborate on that. So n factorial, okay, where n equals the number of objects in the set. Okay, let me, there we go. And n factorial is basically n times n minus 1 times n minus 2 all the way, okay, to 1. Okay, so remember not to go below 1. You'll get 0, and that will not be good because your answer will be 0. So that is basically factorial. And when you work with permutations, it's with order, right? Remember, permutations equals order, okay? The order of a specific set. So anyone taking notes, I'm pretty sure a lot of you have taken notes last class on this, but the difference between permutations and combinations is the order, okay? And I'm going to elaborate on that later. But remember, permutations is arrangement of a specific set, right? So of course order wouldn't matter. So, and that is one of the big key points on this lesson. So for those taking notes, please remember this. It's one of the key points, okay? And combinations, unlike permutations, okay, order does not matter. Let me just say no order, okay, no order. So remember this. Now, why is there no order? Combinations, okay, is basically, we have this set, okay? Let's say A, B, C, and D. Let's take the permutation of this. That'd be 4 factorial, right? That's just the permutation. But we have this set, right? And combinations are sets within sets. Okay, I can say sets within sets. So let's say let's select sets of 2 from this specific set A, B, C, and D. So, okay, sets of 2. See, sets of 2. Okay, so we have this set right here, A, B, C, and D. We want sets of 2 from this set of objects. So, I mean, it can be like A and B, it could be B and D. Okay, it just has to be 2 objects within this set of 4. So it's basically 4, choose 2. Okay, we have 4 objects, you choose 2 of them. Okay, so how do we figure this out? How many sets of 2 are there in this specific set? So does anybody remember our combination formula from last class? Okay, Steven says 6 sets of 2. Very good. Very fast answer. Now let me see if that's correct. So as all of you know, and I'm going to explain this combination formula first before we check the answer. So combination formula, okay, n factorial over r factorial times n minus r factorial, or it was k, okay, n factorial over k factorial over times n minus k factorial. Doesn't matter. Okay. So basically, you just have two variables. Okay. So n factorial is supposed to be the permutation of everything. It's supposed to be the permutation of this bigger set right here. Okay. And as I said earlier, you want to find the permutation of this set before factorial, right? So n right here would, in this case, would be 4. Now R is the how many numbers are in this set you're picking out from it. Okay, so this smaller set right here, it's there. You want to pick sets of 2, right? So R right here would equal 2. Okay, and then we just follow the combination formula. So basically, no order, right? We want to, from this bigger set, we want to pick out sets of 2. And it doesn't matter. You pick out A and B. It's the same as B and A. You don't permutate within those sets that you pick out. Okay? So let's say you pick out a set of 2, B and B. It's the exact same as D and B. It's just no order, right? So in combinations and key point, no order. Permutations, there is order. Okay, so why do we need to divide by r factorial? Okay, so because we're selecting sets of 2, right? We're selecting sets of 2. And 2 factorial or r factorial is basically the permutation of that set you're taking out. So we need to divide by this r factorial because we don't want that permutation. There is no order in combinations. That is why we divide by the order. Okay, so does everybody understand that? Does everybody understand? These are a few key points. Okay, combinations is no order and permutations is order. Okay, so for those who are taking notes on this, please, I'll give you a few moments. Okay. Is everybody done taking notes or not? If you're not done taking notes, you can put it in the chat if you're not done. Is everybody done taking notes? Yes. Okay. So now let's check. Let's see who answered here. Stephen and Frank. Very good. You both answered 6. So basically, we're just going to use the combination formula. So we've already figured out that n equals 4 and r equals 2. So now we just plug it in to the formula. Now that I'm done explaining the formula. Okay. Let's just plug it in. Okay. And basically we get 24 over 2 times 2, which equals 6. Very good. Stephen and Frank. Very good. Very good. So, so now I'm done with this slide. So I'm pretty sure everyone is done taking notes. So let's do some warm-up questions before we advance further. Okay, let's do some warm-up questions. So combinations is mainly the harder one. So let's do a combinations warm-up question. Okay. We have our counting methods here. So I'm gonna reserve this space for our warm-up question. Okay. Right here. Okay, so our warm-up question is going to be here in this square right here. Okay, so our warm-up question is going to be a combination problem. So a lot of students might not get combinations, so this is a great time to see if you understand the material. So we have a set A, B, C, D, E. Okay. in sets of 3. Okay? Pick sets of 3 from the set A, B, C, and D and E. A, B, C, D, and E. Okay. So, and when you're done, please put your answer in the chat, please. I'll give you a few moments. Please start now. And also, I advise you to use the formula I just gave you. Okay, n factorial over r factorial times n minus r factorial. Okay, so are there any answers? 7 comments already. Okay, Steven is the first one. 10. Okay, and Jason also says 10, and Frank as well, 10. Very good. A lot of students are answering today. That's good. That's good. Okay, so basically we do 5 factorial. That's the number of objects in the big set. And then the small set would be 3. Okay, so basically this should come naturally now. Should be pretty easy. Basically 120 over 6 times 2. That is going to be 10. Very good. So now let's go over our counting methods. So our first one would be exclusion. So okay, so I'm gonna use an example to solve this one. So everybody pay attention, please. These two methods are some of the basic methods, but they are very useful, very effective. Okay, so how many 3-digit numbers are there? 3-digit numbers. Okay, so 3-digit numbers. Okay, so we have 3 digits, right? So how do you find this? Okay, and I think actually that won't do. 3 digits, 3-digit numbers. Let me see. Three distinct. Three distinct. Three distinct 3-digit numbers. And you see this word distinct a lot, and that means all the digits are different. Okay, distinct digits with distinct digits. Okay, distinct you will see a lot. Whether it's like finding how many distinct 4-digit numbers are there. So basically distinct digits means that each digit is different. Okay, so let's say you have 420. Okay, there's 4, 2, and 0. That would be a distinct digit, 3-digit number. That is good. What about you have 300? That is not a distinct digit, 3-digit number. Okay, so because you have 2 zeros, right? All digits have to be different. So without further ado, let's jump in. Okay, so exclusion. method. So exclusion method is all possibilities. Okay, all possibilities. So we have all possibilities minus the uh, the unwanted outcomes. Actually, unwanted possibilities. Okay, so basically, exclusion would be all the possibilities. Okay, all three-digit numbers. In this case, all possibilities of three-digit numbers. That'd be 900, right? 900 minus our unwanted possibilities. Okay, our unwanted possibilities would be numbers where where digits are the same. Okay, so our numbers where digits are the same. So like our earlier example, 300, that would be an unwanted possibility because that doesn't have distinct digits. Okay. And right now you can probably see that exclusion is not very effective right here. It's just not very efficient because we need to find all the unwanted possibilities. Okay, but you get the idea. Exclusion is all the possibilities minus the unwanted possibilities. Okay, so here case by case would be a bit more efficient than the exclusion method. Okay, because uh case by case, okay, it's just basically counting all the wanted possibilities. Okay, exclusion is subtracting the unwanted possibilities. Case by case is basically just finding the wanted possibilities. And if you have a lot of cases, if you have a lot of cases, then probably be better to exclude, use exclusion. Because case by case, it's better if you only have one case. Okay, and you understand later when you probably take courses in probability in high school or college. But case by case is just basically finding okay, the actual possibilities. So distinct digit, three-digit numbers. What do we have in store for three-digit numbers? Okay, we have our first digits, our second digit, and our third digit. Okay, this would be the units digit, the ones digit, this would be the tens, this would be the hundreds. So in the hundreds digit, can we have zero? Of course not. We can have 095. That would not be a three-digit number. So usually we would have 0 through 9 as our choices for like the tens digit or the ones digit. But now we can't, we had to exclude 0. 0 is not an option, so 1 through 9, that'd be 9 digits possible. Okay, so next we have our tens digit. How many possibilities do we have? Normally we would have 0 through 9. But right now we need distinct digits. Okay, so you already used a digit for the 100th digit, right? So you out of our tens numbers, we only have 9 left. Okay, now for our ones digit. Okay, and we already used 2 digits, so we only have 8 digits left. And we just multiply these together, and let me check. 9 times 9 times 8 be 648. Okay, so does everybody understand? Are there any questions? Okay. Uh, how I am how I got 900. Okay, Jason, how I got 900. Okay, that was probably in the exclusion. Okay, right. Exclusion. Well, if you go on to Google and you search it up, how many three-digit numbers are there? It's going to be 900 three-digit numbers. That's going to be all possibilities. Okay, all possibilities. Three-digit numbers. Okay, and also if you use our okay, we can actually figure out how many three-digit numbers are there. 10, the hundreds digit, 0 has to be excluded. We have 9. Okay, next we have 10 and 10 because we don't need to count the distinct digits because this is just all possibility, all three-digit numbers. Okay, multiply, you get 900. So next we have the box method, and I'm pretty sure you guys already know it's this. Okay, so you basically find the possibility for each digit, I guess, in this special case of finding three-digit numbers. Okay, you might need a three-digit PIN code. So the possibilities for each pin. So basically, this is very basic. The box method. And you use that a lot, and you use it later in some problems. Okay, so read through these steps on your own first, okay, and then try to interpret them, okay, and I'll explain it after a few moments. Okay, so now that you've probably read through them, okay, so let me explain them. First, of course, you read the problem. For all of these problems I'm going to give you, these are all word problems, okay? And in counting techniques, they don't really give you the formula, okay? It's not like an algebraic uh, linear equation or something like that. They actually give you the equation they need to solve. But counting techniques, you have to interpret the question, okay? And these steps will help guide you in solving. So first, of course, read the problem and read one or two times and make sure you understand. Number two, interpret the question. What are they asking? Okay, that's very basic. And number three, and this is very important. I remember I was explaining exclusion in case by case with this example distinct digit, three-digit numbers. And I concluded that exclusion is not as efficient as case by case. So that is what you do here. You determine your method. Do you want to use exclusion or do you want to use like case by case or box method or permutation of combination? Okay, determine which is the most efficient. You always want to use the most efficient way. Okay, and then use that method to solve the problem. But sometimes maybe you want to combine methods, combine exclusion method, combine permutations or something like that. So make sure our step three is very important. Determine your method. Okay, especially like during a math competition, speed is very important. Okay. Okay. So now let's go on to solving problems. Number one, this might be a bit of a challenge for some of you, but I'm sure you guys can figure something out. So I'm gonna let you guys think for a bit. So number one, try to think of an answer using uh the things that I've taught you. If you don't know, that's totally fine. I'll explain it later. So I'll give you a few moments to try and find the answer of this one and put it in the chat box, please. Okay. So, Frank, you got 2. Are there any more answers? And also, I'll tell you. Uh, okay. And I forgot to tell you this that the boys and girls, they're they're people, right? Each of them are different. You can count them as like different objects. Okay. So boy 1, boy 2, boy 3, boy 4, they're different. Make sure you count that in. So, are there any more answers? Carney says 8. Uh, and Steven says 48. Okay, 48. Okay, a lot of answers. That's good. That's good. And Kaisi says 576. Okay. So, I'll walk you through it. So, first of all, read the problem. Okay, 4 girls and 4 girls, four boys and 4 girls, I mean, are to be seated in a row, right? Okay, find the number of ways they can sit. They have to sit out alternately. Okay, so that means a boy, girl, or girl, boy. Okay, so let's say boy, girl, boy, girl, boy, girl, boy, uh, girl. Okay, so there are 8 seats in total in this row, right? Because there are 4 boys and 4 girls. There are 8 seats in total. Okay? So how many boys are possible? Okay? In this first seat. We have 4 boys, right? We have 4 boys. Okay? 4 boys are possible. Now, this is where the other boy is going to be. Okay? I mean, this is right here is a girl. Okay? So boys. Okay? We already have one sitting in right here, right? So it's gonna be down one now. It's gonna be a 3 right here. Okay. Next, gonna have 2 right here. 2 boys. Okay, possible, and then down to 1 boy. Okay. Same with the girls. 4, 3, 2, 1. So it's basically 4 factorial times 4 factorial, right? It's basically 4 factorial times 4 factorial because the 4 boys right here can permutate themselves, right? And the girls can also permutate themselves. So it's basically 4 factorial times 4 factorial, but that is not the answer. It's not 4 factorial times 4 factorial. Not at all. Okay? And what is 4 factorial times 4 factorial anyways? 4 factorial is 24, which squared. 526. I mean 576. Okay, Kai, see, I think you said 576. Very close, very close. You did 4 factorial times 4 factorial part. But make sure because it's not always going to be boy, girl, boy, girl. You can have girl, boy, right? That is also a possibility. So when you're solving problems like these, make sure you count girl, boy, or boy, girl, which one you miss. Okay. For girl, boy. Okay, we're going to have the same thing, 4 factorial times 4 factorial, but right here we just add them, right? So 576 plus 576 is going to be 1,152. Okay? So does everybody understand how I got this? Okay, Kaisi, very good work. You got very close to the answer. Okay, yes, Stephen says. Yes, very good, Stephen. Okay. Uh, so if everybody understands, I will go to the next problem. So number 2 is how many distinct permutations can be formed from all the letters of competition? Okay, how many letters? Okay, how many letters are there first of all? Okay, and I'm gonna solve this for you. Okay, because this is a bit of a new problem, and I'm gonna sometimes actually a lot of times you come up with problems like this. I'm pretty sure. Okay, I did math counts. Okay, I've done math counts a lot of years. Okay, so math competition, really great. Okay, maybe you should check it out if you're interested. Math counts. Okay, and I think this was a problem once in math counts. Okay, so this is very important. Make sure you understand this one. Okay, and this is actually a pretty popular question. Okay, so number 2, I'll solve for you. So competition. How many numbers are there? I mean, letters are there, anyways. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Am I correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, 11 letters. Okay, so basically distinct permutations, right? 11 factorial, right? Totally 11 factorial. But we can have, okay, look how many same letters we have, right? Okay, so a distinct permutation of competition would just be competition, right? It'd just be competition. Okay, and my handwriting is bad. Okay, competition. That would just be a permutation of competition on its own. But look how many I's and T's are there. There's 2 T's, T1 and T2. So basically, there can actually be 2 permutations for this, right? There can actually be 2. So the second permutation for this would just be T1 and T2 are switched, right? But we want distinct permutations. Remember what distinct means, okay? These permutations can't be the same. Okay, so maybe we switch T2 and T1, but unlike our boys and girls, they are different, right? I mean, okay, boys and girls are different, right? And letters are the same. They're the exact same, T1 and T2. Okay, so we have 2 T's, right? And like I said, order does not matter in this specific problem because no matter how you permutate these 2 T's, they're gonna look the exact same. Okay, they're gonna look the exact same. So basically, from 11 factorial, you're going to divide 2 factorial. Okay, because we divide the permutation of these 2 T's. Now, what other same letters do we have? Okay, we have T1 and T2, right? Okay, and then we have I1 and I2. Okay, another 2 factorial. And then what do we have? I think we have O1 and O2, okay? So this will be our answer, okay? We divide the permutation of all of these. Okay? So make sure these letters do not repeat and look the same. Now, if this was just permutations, of course, this would just be 11 factorial, but in this case, we want distinct permutations, okay? We want distinct permutations. This word distinct will show up a lot of times, okay? So 11 factorial over 2 factorial, times 2 factorial times 2 factorial. So that will be a lot. That's all I can say. So let me actually solve this one, okay? So what is 11 factorial times? Okay. So and this will actually come up a lot. Okay, these problems. So let me solve. 11 is basically 11 factorial over 2 times 2 times 2, which is 8. And let's see. Okay. I'm pretty sure we can simplify this factorial, but I'm just going to. If you have a calculator, just go to the calculator and find out what 11 factorial is. Much easier. Okay, that's very big. Hey, 4,989,600. Okay? A lot of permutations of competition. A lot. Okay? So does aside from the big numbers, does everybody understand the concept? Okay? Everybody understand the concept here? Okay, yes. Very good. Very good. And now, number 3. Please do this on your own using the same method. Okay? I'll give you a few moments. Okay. Steven, you do not have a calculator? Okay, maybe you need to go to Google and use the Google calculator. But you're still doing really good without a calculator, so. And this, Jason, you're legit learning Algebra 1 and this is not in your curriculum. Why? Because this is not algebra. This is counting techniques and probability. And, oh my god. It is the same answer again. Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh shoot. It is actually 11 letters again. ah. And how many, but let's actually solve this nonetheless. Yes, I think it is the exact same answer, actually, because we have 11 letters, right? 11 letters, and see here, M, A, and T are the same. That'd be the same answer. Ah, same answer. Uh, okay, same answer. Okay, from that aside, uh, let's go to the next problem. So this one, there are two main methods, okay? And as I said, please pick the most efficient one, okay? No, step 3, okay? Let's go back to step 3. What is that? Determine the method, okay? There are actually two methods to solve this one, okay? Determine the most efficient one, okay? So number 4, let's read the problem first, okay? And you can read it with me and actually solve it while I'm reading it, but okay. I'm going to read it for you, and please put your answer in the chat when you're done with the question. From city A to city B, there are 7 train stations, which are including the stations at city A and city B. So, okay, we have A and B. Okay, we're including that. So basically, there's going to be 7 train stations in between. So 1, 1, 2, 3, 4, 5. Okay, so 5 train stations right here. Okay, and A and B are also stations. Okay, so for every pair of stations, okay, 1 ticket is needed. Okay, for example, station B to station C. Okay, and okay, let's say, actually, let's not say station B to station C. Okay, it's going to be station 1 to station 2. Okay, so this is 1, 2, 3, 4, and 5, and station A to B are also stations. Okay, so station 1 to station 2. Okay, that can be a possibility, and 1 ticket is needed. Okay, so station 2. Okay, 2 to 1 is the exact same thing. Okay, it's the same thing as 1 to 2. Okay, so remember to divide by 2. Okay, because we don't count our permutations here. Okay, we don't count our order here, and I just gave you a really big hint. We don't count the order here. You might already figure out what method you're going to use. So basically, we want a pair. Okay, a pair of stations, and 1 ticket is needed for every pair of stations. Say station station 3 to station 5. Okay, that is also possible, or station 3 to even station B. Okay, that is also possible, but B to 3, 3 to B are the same exact thing. So don't count more than you need. So how many tickets are possible now that I'm done explaining? So please put in the chat. And yes, Jason, I have a mistake here. A mistake. Sorry for that. That is the other parentheses. Thank you for noticing. Uh, Steven says 21. Very, very good. Okay. Very good, Steven. Very good. That was a very fast answer. Very good, Steven. You're doing extremely well in this class. And also others, Jason and Frank, you're also doing pretty well. Okay? So congratulations to you all. Any more answers? No answers? Then I'll solve it now. So basically, there are 2 methods, and let's do 1 method, and this is the most efficient way. Okay? And remember when I said order does not matter in this problem, and that was a super big hint, because when you think of order does not matter, okay, that's a key point. Okay, you think of combinations, right? And you have 7 train stations, right? You have 7 train stations. And you want to pick out pairs of train stations, okay? And what is that starting to look like? That is starting to look like 7 train stations. Pick 2 train stations, okay? And that is looking a lot like combinations, right? So it's basically going to be 7 factorial. Choose 2. Okay, choose 2 stations. Okay, so 7 factorial divided by 2 factorial times 5 factorial. Okay, what is that? 21 it is. Okay, and that is our answer. Okay, so Stephen and Jason, which did you use this method to this combination formula to find the answer, or did you use another method? So please put in the chat what method you used. Okay, which method you used. Okay, my method. Okay, Jason, you use my method. Very good, because my method is the most efficient one. Okay. And x times x minus 1 divided by 2. Stephen, very good. You used another method. And as I said, there are two methods, and Stephen's method is a second method. Okay. It is uh that's a second method, and I said that method isn't as efficient, but this combination method is a little bit faster. It's a little bit. Both methods are very good. And Stephen, you congratulations for figuring out that. Uh, so basically, like what we have here, and okay. Uh, Stephen, x times x minus 1. Are you sure that is correct, Stephen? Are you sure it's not x plus x minus 1 plus x minus 2? Because if you multiply 7 times 6 times 5, isn't that going to be 7 factorial divided by 2? That would be a bit big, don't you agree? The second method, it would be 7 plus 6 plus 5 plus 4, right? You start out with 7 train stations. Actually, 6. Yeah, 6 plus 5. Okay, I'm gonna elaborate on this. Okay, so you have to start with 7 train stations, A to B. Okay, so basically, how many possibilities? How many pairs? And this is like the handshake problem. You probably learned the handshake problem. There are 5 people in a room, or how many people are in a room? There are 5 people in a room, 10 people in a room. How many handshakes can be made? It's basically how many pairs can be made with A. So A can go to 1, okay, A can go to 1, go to 2, go to 3, go to 4, go to 5, go to B, okay. What about 1? 1 cannot go to A because it's already going to A, can go to 2, can go to 3, can go to 4, can go to 5, can go to B. What about 2? Cannot go to 1 or A because it has already gone to, okay, 1 and A. Go to 2, can go to 3, can go to 4, go to 5, go to B, and you get the idea, okay? You get the idea. So basically, our first one, we have 7 train stations. A can make 6 pairs because it's not including itself. A, okay? So it's basically going to be 6 plus 5 plus 4 plus 3 plus 2 plus 1. Now, what is that? What is that? Okay, 7 times 3, that'd be 21. This would be 21. Okay? Yep, and that is going to be 21. And Stephen, okay, please explain your method for me because I did not think of your method. Stephen, it is only for 2 selections. It works only when it is a pair. Okay, so please elaborate on your method. Very unique. Very good. So, are you done elaborating or explaining your method yet? It is indeed very unique. I haven't thought of it, so congratulations to you. Uh, Anyways, so still working on it. So there's 7 choices for the first one, okay, and 6 choices for the second one, and okay, 7 choices for the first one, and 6 choices for the second one, okay. Right. That is, I think that works. Good job. I think I get it now. Very good, Steven. That is very good method. But that is also pretty efficient, I think. So very good, Steven, on making a new method. Very good, very good. So number 5, okay. And I do have two number 5s. Okay, this would be 6. Whoever that figured that out, I think it was Jason or someone else. Thank you for finding out my mistakes. So anyways, number 5. Consider all 3-digit numbers with distinct digits. Each digit is different. Okay. Okay, as I said, distinct digits. Each digit is different. Okay, we don't have much time left. So please make sure you work efficiently on this one. So, I'll give you a few moments to try and find all the 3-digit numbers that have distinct digits. Okay, they have to be different. Okay, distinct digits. And how many are odd? How many odd 3-digit numbers have distinct digits? Okay, make sure. Pay attention to distinct. So, okay. Uh, in Steven says 60. Okay, and Carney says 9 times 10 times 4. That is bigger than 60. Okay, so we have different answers here. Steven, are you sure it is 60? Because we have three 3-digit numbers, okay? Make sure to check if your answer is reasonable. 3-digit numbers, okay? We have 900 of them. And if we have distinct digits, we have 648 of them. And how many are odd? Okay. Might want to check your answer, Steven. Okay. And also, you learned it in 3rd grade. Wow, that's impressive, Steven. Very good. So you're familiar with it. And I'll give you a few moments to try and figure this out. Okay? Okay, so 2 more comments. Oh, Steven says, you're sure. Okay. Then I'll help for you then. Okay, so 5th grade. 5th. Uh, Yep, I know which method I'm going to use for this one. Okay, and I'll use case by case. Actually, I'll use case by case. It's better, I think. It's more efficient. Okay, if I use exclusion, it might get it might get a bit difficult to keep up with. So I'll use case by case for this one. Okay, so it all depends on the last digit. Okay, Because if you want a number to be odd, what does it have to be? The last digit has to be odd, right? If the last digit is even, then it's gonna be an even number. If let's say the last digit is 6, of course it's gonna be even. Okay, so the last digit has to be odd. Okay, I don't care what the first, second digits are. The last digit has to be odd. So 0 through 9. What odd numbers do we have? Okay, what odd numbers do we have? So I'm like 1, 3, 5, uh, not 6, 7 and 9. Okay, 7 and 9. Okay. So, uh, 1, 3, 5, 7, and 9. Okay, so we have 5 odd digits, right? Okay, we have 5 of them. So normally, okay, now that we've figured out our last digit, let's go on to the first and second digit. And that depends because now that we've used one digit, one odd digit, we only have like so many digits left. Okay, so how many digits usually we have for the first digit? Okay, we have 9, right? 1 through 9 because we can't use 0. 1 through 9, but we already used the digit, so it's gonna be 8. Now we used 2 digits already. It's gonna be another 8 because usually this would be 10, right? Usually this would be 10, but now we're working with distinct digits. We already used 2 digits. Okay, so that will be our answer. 8 times 5. Yes, that would be 320. Okay? So, okay. Steven, you thought all digits must be odd. Okay. But if all digits must be odd, then uh let's say you have let- if all digits must be odd, your answer is actually correct. Huh. So 60 is actually correct because it would be 5 times 4 times 3. So you are actually correct, Stephen. Uh, but in this specific problem right here, okay, we want 3-digit numbers that are odd, okay? Because if you want a number to be odd, you actually just have to be the last digit has to be odd, okay? Uh, so let's go on to number 6, and this is like the exact same problem, except how many are even, okay? And we're almost like we're a bit over time already. So okay, bit over time already. Sorry for that. Okay, but basically, if we already figured out how many are odd, so if we just want to figure out how many are even, we just use exclusion, right? All possibilities are going to be 900 minus our unwanted ones. Okay, all actually that's wrong, not 900 because we are considering the 3-digit numbers with distinct digits, which is gonna be 648 minus our odd digits is gonna be 320, which equals 380. Wait, no, that is 28. Okay. Sorry for that little mistake there. 328 would be our answer for all even numbers. Okay. Basically, we already figured out all numbers. Okay. Then we basically just use exclusion, right? It wouldn't be that smart to go case by case here because since we already have the odd numbers, let's just use them, right? And if you just make some quick mental calculations, you get 328. So that was our last problem. So thank you for listening, everybody. Okay, and make sure to check out this video on YouTube if you have any questions. Okay.